Okay, so I have a couple of slides to start out with here, just as sort of an overview and sort of a little bit of background information, and then the bulk of the time here, hopefully we'll be able to do real-time, I'll be able to do a real-time demo. We'll see exactly how well that works. So just in case you need to know, so sort of background information is, what is a mosaic? So in astronomical speak, it means probably what you think it means. It's a larger picture composed of many smaller pictures. So some telescopes have relatively small fields of view, and some are used to tile a much larger region. So I'll probably refer to the FITS images that we'll be working with shortly as images or possibly mosaics, depending on their parentage and what I know, where I know they came from. But the whole point of doing a mosaic is that you can get an image of a region much larger than a single pointing of the telescope. So for example, Spitzer IRAC, the instrument called IRAC on Spitzer, its field of view is 5 arc minutes on a side, and I've worked with a map that's covered 10 square degrees, but you need 21,000 individual frames. You can do it, it just takes a long time. I've put at the bottom of the PowerPoint slides here a link to the corresponding page on the Cool Wiki if you want to go get more information. So what is a FITS file? FITS is Flexible Image Transport System, and it really is what professional astronomers use to transfer images back and forth between telescopes across wavelengths. Astronomers all over the field use FITS images. And what it is a plain text header and then a bunch of binary data that's the image. So if you actually try to open a FITS file with a plain text editor, it will get started. It will try, because the first several lines of the file are plain text, but then it will gag when it gets to the binary parts of the image. So the header, at the very least, has some really basic information to tell the computer what size the image is that's coming and whether or not that image has coordinates attached to it. WCS stands for World Coordinate System, and it's how ds9 or any other FITS viewer translates between the pixels that are in that image into right ascension and declination. So the header at the very least tends to have that kind of information. Some headers are very, very long because they may also contain all sorts of things, including the target, the telescope, the wavelength, the astronomer, the date it was observed, when, exactly when in universal time the image was exposed, sometimes in a variety of different time keeping mechanisms. Sometimes also you get a whole history of all the data reduction steps. Everything that anyone has done to that image usually leaves some trace of it in the FITS header. So the FITS header can be very, very long, but also very, very useful, because it's where you go to find out, things like the date it was observed. Because if you're looking for something that changes in the sky, the date of observation is really important. The binary image itself can be a single plane. In other words, it can be just, one image, one right ascension declination image. But it can also have something called extensions or planes. So in other words, you may have one FITS file that has the image, the errors, the coverage, all sorts of other information on many planes of data in that FITS file. And ds9 handles it elegantly. Some other FITS viewers you may be aware of might not handle multi-plane FITS files. So, but it does, when you try to load a multi-plane FITS file into ds9, it asks you which layer would you like. The image, ds9 can also handle a spectrum, although it treats it as a single pixel wide image. It can also handle a stack of spectra, which show up as, stripes basically. The image, you can also have FITS binary tables. I don't know exactly what ds9 does with that. I suspect it gags and says it can't open the file, but you can actually transfer fairly large tables of data using FITS format, although that's less common than just a regular image from the sky. So why even bother with FITS when there's so many other options like JPEGs or GIFs? FITS images are at least 16, sometimes even 32 bits deep, and by that I mean each pixel on the screen has within it 2 to the power of 16 or 2 to the power of 32 different possible levels of numbers in each of those pixels. So it can be, at least 65,536 different shades of gray possible, possibly 4.3 billion possible discrete levels of data for each and every pixel on the screen. The images that are more common, like JPEGs, GIFs, and PNGs, they're only 8 bits deep, which means there's only 256 shades of gray in each pixel. So that's why we'll talk about this more when I actually do it in a few minutes. If you make a really nice image that looks really great on the screen, where you have lots of shades of gray or red or whatever color scheme you pick, and you go to save it as a JPEG, the resultant JPEG looks awful. And the reason for that is the computer is compressing 65,536 levels per color plane into just 256. And so that's one of the main reasons why you use FITS rather than anything else, is that it has such a deep range, just a wide range of capabilities of representation of numbers. That's why. And for astronomical images, you need that kind of dynamic range. You need that variety of discrete values. So if you are sitting down to do science, and you find yourself looking at a JPEG, a PNG, or a GIF, stop and go find the FITS file, because the JPEGs, the PNGs, the GIFs are going to lose information compared to what you get in the FITS file. So a bigger picture sort of thing of why images matter. I mean, you all know that a picture is worth 1,000 words, and it really is a very easy way to quickly absorb a lot of information. And I mention this specifically because there's a lot of catalogs out there already. We talked about the WISE catalog in the last NITARP tutorial, and they've already done a lot of the quantitative measurements for you. But just because the computer says it does not mean it's right. You really do need to go back and check the images, even if you're working with somebody else's catalog. So it really does matter to anyone doing astronomy to go look at the images, even if somebody else has already made the quantitative measurements for you. Also, it turns out there's distortion in every camera, everywhere. Your iPhone does too. There's a picture of my son at a drum concert a couple weekends ago. That stick is not really curved. That's what my iPhone distortion does. So every camera everywhere, including astronomical cameras, have distortion. And the mapping between pixels and right ascension and declination on the sky is rarely simple and straightforward. It's rarely the case that you can take 3 steps in pixels and have it be exactly 3 steps in right ascension. So especially when you're moving in different, having large chunks of sky. So image viewers, anything that reads a FITS file is capable of doing that complex calculation for you, so that you can really easily and transparently put your mouse over the image and find what right ascension and declination any given pixel is. But it needs that WCS, that World Coordinate System, in order to do that. So why use ds9 at all? It's free and powerful. You can find it in a wide variety of platforms. You can make a quantitative measurements that are research quality with it. And it is very flexible. It can handle just about any FITS file you throw at it, as long as you have enough memory. I just wanted to mention that you can actually view spectra this way. Certainly when you're at the telescope taking spectra, I have used ds9 constantly during an observing run to make sure that the images I'm recording of the spectra themselves are valid. But in order to actually do data reduction and inspect the spectra, we actually use ds9 in conjunction with other tools like IRAF. Chances are excellent, whatever team you're on, that this is the go-to tool for your mentor astronomer to inspect images. They may do more sophisticated analysis using other tools, but it is just a workhorse. Just about every astronomer everywhere knows how to use ds9. So there are other alternatives out there. For completeness, I wanted to mention this, and also the WISE folks at Berkeley have a nice list of a variety of these options and pros and cons. You may be familiar with ImageJ, SalsaJ, even GIMP and Photoshop. None of those are developed for astronomy. Some of them will let you do with things, but they're not as flexible in terms of astronomical applications as certainly other applications are. And GIMP and Photoshop certainly aren't going to let you make really valid quantitative measurements. I don't know very much about Micro Observatory Image. It's a relatively new package, but the WISE Berkeley site says it can't handle WISE images, which, may limit its utility until they fix that. There's certainly tons of amateur packages out there like MaxMDL. Obviously, those were developed in the context of doing astronomy, but from the limited experience I have with some of these packages, they tend to be more focused on actually running a telescope and simply getting a FITS image out, as opposed to doing really research quality analysis. So for all of these reasons, I would recommend going to ds9 or some other professional astronomy tool to do the kinds of work that you might be doing. So where to get it, some of you who are on early, watch me actually do this, because I didn't have the slide up before. If you Google ds9 astronomy, you'll find it. If you just Google ds9, you'll find the episode guide for the Star Trek series. The website is given there. They have new releases all the time, new features all the time. I can't even keep up with it all. I'm just going to give you sort of a baseline introduction here, sort of the basic features, but I'm sure there's more that I haven't, that I don't use because I don't know about it. And I've already alluded to this. Why is it called ds9? So originally, our programmers at the Smithsonian Astrophysical Observatory developed this tool, this image viewer, and they called it SAO image because they were at SAO and it was designed to deal with images. So in a few years, technology had changed enough, software had changed enough that they decided to completely rewrite it from the beginning, different language, and so they started calling it SAO image the next generation, or TNG. Then in another few years, technology changed again, so they decided to make it another overhaul. And what comes after TNG? DS9, because Deep Space Nine is the series that came out for Star Trek after The Next Generation. So that's the history of it. Okay? So it really, hopefully, is not scary once you know that. Okay?